So far we have seen the concept of adaptive filtering and how algorithms like least mean squares could be used for applications like adaptive noise cancellation and also in doing adaptive segmentation. There is another interesting possibility in using adaptive filters, and that's in the area of prediction, to be specific in linear prediction. So we are familiar with this, the block diagram, in which the input signal entering, you get the output signal Y, then you have a desired response D, and the error function E, and the optimal weights or the filter coefficients were W. So this is a familiar configuration in designing an adaptive filter, and essentially there were two inputs going into an adaptive filter. One is the signal X, and other one what was called the desired response D. The assumption is that the desired response D should have some sort of correlation with the input signal X for the adaptive filter to work. The whole idea was in optimizing E by using least squares technique. Then it happened that the optimal filter coefficients W could be obtained as R inverse P matrix. R matrix corresponds to the autocorrelation values of the input signal X, and P is a matrix that determines the cross correlation between the signal X and D. So this is what we have seen before, and just by changing this input in suitable ways, we could achieve some very interesting adaptive filtering properties. One example we saw was removing mother's ECG from fetal, which could also be expanded to other domains of physiological interference removal, mainly when the two signals have a significant overlap, both in the time domain as well as in the frequency or the spectral domain. So now using this concept, we can have other real interesting variations to what we have seen so far. One such possibility is what's called prediction. Prediction, for example, if we were to have these discrete samples for the time being, let's assume these discrete samples, the red points here. And when you look into the red points, if you just look into those 5 red points, by eyeballing those red dots, you could predict what the next sample would be, because our brain does some kind of an interpolation, and it can say to some extent that the next sample, the green color, would be here, okay? Because we have used the past samples of the red dot, and it kind of gives an idea. It's following some kind of a sinusoidal shape. So the next point would be where we denote it here. Now I could use this green point further, and I can take the past values and predict the next one. So we can keep doing it, okay? So this is a very well-known mathematical function, which is sine, and the prediction was pretty straightforward. But in cases of biomedical signals, how do we imitate this kind of a process? How do we bring this prediction around? In other words, how can we predict the next value of the signal given the past values of the signal? So if you give the past values of the signal, let's assume the signal xn, the past values are xn minus 1, xn minus 2, and so forth. So these are kind of the current and the past values of the signal, and the future sample could be xn plus 1, okay? Now, given these past samples, how can we predict xn plus 1 is the question here. Okay, mathematically speaking, that particular graphical illustration could be represented in this way. So now it's coming to the point of prediction. Just by looking into the configuration of the filter diagram we had, it's just by playing around with your desired response, we can make this filter do a proper prediction after the error has been minimized, so that the output of the filter Y would always be the next sample. Okay, so that's possible if I make my desired response to the next sample xn plus 1. Okay, I can do that thing because if the xn is what's entering the filter, each time when a sample enters, it does have m minus 1 past values, because this filter is an mth order filter. So just by how xn minus 1, xn minus 2, all the way up to xn minus m plus 1 samples would be residing at each time instant in the filter. Now the desired response, previously we didn't have a good idea about desired response, but when we did the adaptive noise cancellation, we configured the desired response in a way that will help us to get a better fetal ECG representation. So similarly, in this prediction concept, it's very simple and straightforward, that we have made the desired response to be the signal itself, but its future sample. Okay, so this also means that we could also see, if I put the desired response xn, here it could be xn minus 1 and so forth. Okay, so basically if you have the past samples entering the filter, it will give the next sample predicted. Okay, so this is how a linear predictor could be designed by using the similar adaptive filtering concept we have seen before. Once a filter is converged, what happens is that this, after it has converged or the error has been optimized, then you don't need the desired response anymore. The filter has learned. That's what we call. So when you send the signal xn, for example, the output would be automatically xn plus 1, because the filter coefficients are trained to predict the next coefficient. Okay. But note, in signal processing, normally we don't put n plus 1 because it really doesn't go with the causality concept. So it's just an idea that normally we assume that the thing that's entering is x minus 1 and what we are getting is xn. So because n plus 1 is typically avoided as a notation in signal processing. Okay, it could be in other areas, but in signal processing we try to avoid it. Okay, so that's the whole thing here. Now we are asking the filter to predict the next sample for us based on the past values. We know if it was a very deterministic function like a sine wave, we can eyeball and we can do it, but can we make the system to predict a signal which may not have a very well-defined mathematical formulation like the sine wave, specifically biomedical signal? So that leads to the concept of linear prediction. And linear prediction is just a simplified form of the adaptive filter concept we saw, where it is a special case of the adaptive filter in which the desired response is the next sample of the signal. Once it's trained, then the filter can start predicting the subsequent samples based on the past samples, and that's what leads to linear prediction. Now, the same block diagram I showed before, this block diagram which we just saw before, of desired response and your xn could be rearranged in a much more compact way without a loss of any assumptions here. Okay, so same thing. So what's happening is that this is the diagram of a linear predictor. It's a familiar diagram like what we have seen before. So if you see the role of the desired response of the xn, will play the role of dn, and what's entering into the filter, the very first coefficient is xn minus 1 after this delay element. Here it would be xn minus 2 and so forth, and here it would be, the final value would be xn minus p, where p is the order of the filter or order of the predictor here. Okay, so that's the thing. So what's entering into each of the things is that we will see that very soon, the convolution expression of the output of the filter. So in other words, this part is a role that's played by the predictor or the filter, and anything outside this dotted lines, especially the xn entering the system, is played by the role of dn. So essentially, this error function is trying to minimize the difference between the dn and the output of the filter or the predictor here. So the name is interchangeably used. So what is the output of the predictor here is x hat n, and the x hat n, the summation of the x hat n goes from k equal to 1 to p, okay, alpha k xn minus k, okay. So previously you would have seen the convolution expression going from 0 to whatever m minus 1 or 0 to p minus 1, but here we are going from 1 to p. It's because we wanted to predict the next sample, okay. So on the basis of the past samples, like here it would be xn minus 1, xn minus 2, all the way up to xn, using the past samples, how would I predict the xn, the next sample, okay. So that's why it's reformulated like this. On the other hand, let's say if you used k equal to 0 to p minus 1 rather than 1 to p, then we should be making sure this is nothing but xn plus 1, okay. And as I said, we try to avoid the xn plus 1. That's why we are going from k equal to 1 to p rather than k equal to 0 to p minus 1 in this convolution expression, okay. So this is simple convolution, which is the output of this guy. And the order of the filter is P. Now, you might be wondering why I have used alpha here instead of previous things like W. In adaptive filter, we used W for the filter impulse response of the filter coefficients. Before that, we were using H for filter coefficients and for representing the impulse response of a filter. Now we are using alpha, okay. So the alpha coefficients are called the predictor coefficients, okay. Just as a recap, previously we used W and H. So they all represent the same functionality, okay. They all represent the impulse response of the filter, or it's kind of the characteristic of that system, okay. It's just to make sure that we understand the differences between the filters. H was meant for fixed filtering, W was meant for adaptive filter, and alpha is a special case of adaptive filter, which is a predictor here, okay. Nothing else is different. The same thing happens here. The filter coefficients are as part of the multiplier system, and they get multiplied by the delay elements and it added. So it's again multiplication accumulation operation, which is nothing but the convolution expression here. Now, once we have this thing, it goes back to the similar steps as adaptive filter design. Nothing is different. All we have to do is that we have to minimize the error function. So in other words, so this is the output of the filter that we just talked about, equation 1. Then the error of this filter right now is the difference between xn minus x hat n, which is the output of the filter. Previously, we had, in the case of adaptive filter, we had the desired response minus the output of the filter. Here, as we know, the desired response xn, so it's xn minus x hat n, okay? As simple as that. And expanding that becomes like this expression. Now, once we have the error, we always have to remember in this particular filter design problem, unlike using Z transform or Laplace transform, in adaptive filters, we try to minimize the error. In other words, error square function, we try to minimize the error square function by taking the gradient or the differentiation operator. In other words, we do have a parabolic surface or a paraboloid surface, and we are trying to find the minimum point. So we always take the differentiation or the gradient operation and we make it equal to 0. Similar to adaptive filter, we are doing the same operation here. Now, following the same steps, nothing is different. You know, if you're familiar with adaptive filtering steps, now making this partial differentiation, because we have to do with respect to each of the filter coefficients. In other words, we have to do with P of those filter coefficients. That's why it's partial differentiation operation, and that's the reason we call it gradient, because we are working on an alpha, which is not necessarily one quantity, it's a vector. Okay, the P of those are there. When we use this expression, equation 4, it turns out that this formulation becomes like this. And if you look very closely into this expression, you will realize the terms are now starting to look familiar. This term, for example, is nothing but the autocorrelation value of the signal. Again, this term Here, because we have the desired response to be signal itself, is also an autocorrelation term. Okay. Now, just by substituting them to be autocorrelation terms, now we have P of those, and as we indicated in adaptive filter design problem before, we could put that into a matrix notation like this. So the whole algebraic expression which we just talked in the previous equation could be equation 5, for example, could be written in a convenient matrix form without any loss of information. Equation 5 could be rewritten into equation 9 in a matrix form. And this matrix form is similar to the previous matrix form we had, but the only difference is here R alpha is equal to P. As I said previously, remember R W equal to P, but here R alpha is equal to P, the same concept. But interestingly, here P happens to be an autocorrelation matrix of the signal itself, because it's nothing but the signal that's the desired response. And that's why we have a small r here. Keep in mind, if you look into this equation carefully, the equation 9, in the autocorrelation matrix, we have Rxx0, Rxx1, and so forth in the first row. And the second row, it's similar, but it kind of circularly gets rotated. Typically in an autocorrelation matrix, the main diagonal, the subdiagonal elements are the same. Okay, that comes back from the algebraic expression that we had in equation 5. If you expand, you will end up in this formulation. But what's on the right-hand side of this equation is that you got to be careful that here it's a cross correlation of the desired response and the signal input X. But here we are doing the cross correlation between Xn and Xn minus 1, Xn minus 2, and so forth. Okay, so that's why this particular matrix starts from a lag of 1. So it's autocorrelation again, but it starts from lag of 1, 2, 3, and so forth. Okay, and we could call that as a small autocorrelation matrix R. Okay, so it's no more a P, a cross correlation matrix, because in the predictor problem, because we are predicting the subsequent samples of the signal itself, the cross correlation matrix P becomes a small R, which is an autocorrelation matrix of the signal, but at lags which are non-zero. Okay, it's not the signal multiplied with itself. It's delayed by 1 unit, 2 unit, and so forth, and we take those values. So it's the same thing. Nothing has changed from what we have seen before, but this has become, now the alphas have become, once we determine, the alphas are acting like a predictor. So if we send your signal X into this filter with alpha as values, it will give us the next sample and so forth. Okay, so that is a very neat concept. And why this is important, why predicting the next sample is important, is going to be the next key step to keep in mind. But I also have other equations like equation 6, 7, and 8. They're essentially pointing out to what's happening to the error function. Okay, and it's again a simple substitution of the autocorrelation values, and when you go through the math, it will be very obvious for you what's happening in equation 6 to 8. It's just for your understanding, but the key equation here is the R alpha is equal to small r expression. Okay, just like how we had the previous one, this equation 11 is a key outcome, and alpha becomes R inverse times small r. And we know when the matrix inversion is not easy, then we could follow techniques like least mean square to get the estimate of alpha, just like how we discussed on how to get the W from the adaptive filter concept. Okay, so you got to treat this as a very special case of your adaptive filter concept. Okay, now why would this be very important? In addition to predicting, the predicting is sounding like a magic and fun. In addition to predicting, this has very deep applications in key areas such as modeling. We will see that very soon, what specifically time series modeling or mathematical modeling. Modeling is seen as an important part of feature extraction and a representation of the signal with fewer coefficients. Okay, we will come to that point. It is very valuable in spectral estimation properties. And finally, it's useful in data compression and low bitrate coding. So it has all those applications. Now the filter, which is been turned into a predictor, now this predictor has all these applications. So this is where we are starting to connect the dots of the various things we have seen in the course on how the filter will start to become like a model parameter or a feature, and how this feature could be used for pattern classification and machine learning applications. They're all getting interrelated with the special case of this predictor concept based on alphas. Okay, so there are these three important applications, and that's exactly what we're going to see for the remaining part of this module. In terms of time series modeling, that's the first application, let's call for linear prediction or LP application, is in the time series modeling. To be more specific, some people call it even mathematical modeling. Okay, mathematical models have so much convenience in biomedical context. It allows us to understand the system property in terms of mathematics, and we have done to some extent before when we did some simple feature extraction. It was kind of a mathematical representation of the signal, but very fewer coefficients or very few dimensions, so that it could be treated as features for a follow-up machine learning. But is there a theory of extracting those features in a much more systematic way? That's exactly this mathematical modeling concept would be. Time series modeling means it's useful for any signal like biomedical signal, which are essentially time varying signal that are sampled and digitized, which also means if you have another time domain data like stock market index or any other form of time domain data, it could be applied as well. So such signals like biomedical signals and financial signals are called as time series signals, okay, whichever has a time as the x-axis. Okay, so with that, the global expression of the mathematical modeling is very familiar to what you're seen in the first part of the course. Okay, so this expression you see, we are assuming the signal, which is the signal to be modeled, which could be a biomedical signal. It could be an EMG signal or ECG or any biomedical signal that we need to model. Why modeling is important? Again, as I pointed out, it allows us to extract the features in a much more systematic way. Okay, so here the signal is assumed to be xn. We are saying the signal xn can be represented as a linear combination, of its past values. Okay, so k equal to 1 to p ak x of n minus k. So it's a linear combination of its past values. So you see in this course, or in general in signal processing, repeatedly you see operations like delay, multiplication, and addition. Same thing happening here. Your signal xn is delayed, it's multiplied by a case, and it is added, summed it together. Okay, p of those in this case. Okay, so it's a weighted combination of its past values. Important to keep in mind, because it's past values, I'm starting the summation from k equal to 1 to p ak xn minus k. There is a reason to have the negative sign outside. We will know that later. Plus g, which is just a constant. Okay, it's called the gain parameter. It's a constant g. Summation your L going from 0 to Q, BLUN minus L. Okay, so again similar to that, but what is UN? Is basically you are assuming UN to be a hypothetical input to the system. Okay, hypothetical input to the system. Okay, so if I put the block diagram of this particular thing, we are assuming there is an hypothetical input UN going into the system, and that's generating your signal xn. Okay, and in this course we have seen repeatedly this kind of a block diagram configuration, but here xn, as I said, is denoting your physiological signal that you can detect at the surface of the body. Okay, xn it could be your ECG, for example. UN is the input trigger that's basically generating the signal xn. So in other words, none of our biomedical signals are generated without a cause. They have something going on inside the body. That's why it's manifested on the surface of the body. So we know, as a biomedical engineers, we know most of the physiological signals are generated because of the action potential of the cells. They get summed in a way that we understand in some cases. In many cases, we don't know how the action potentials get added. But nevertheless, that action potential is eventually manifested as the signal that we are detecting at the surface. So that particular input to the system in a biomedical context, we can assume to be hypothetical input U of n, okay, U of n. So now we are modeling that the whole system, which is triggering your input in the biomedical context, and the signal that we are sensing at the body with a system like this, or with a filter like that, which will have this kind of an expression. Basically, we are saying the output of the filter xn is nothing but the past values of the output of the filter added plus the value of the hypothetical input. Okay. Now, all we know is that whenever you have an input output, we know from our previous knowledge, I can always write the transfer function of this system as h of z, and that transfer function h of z, which is also given here, is nothing but your output by input. Output tends to be x. Now we have to take the z transform of that, and the input is u of z, which is a hypothetical input. Now it happens that this becomes very much easy to follow now, because I'm just doing the z transform of equation 1, and it happens like the h of z. In other words, the system transfer function is given by the numerator, which is nothing but 1 plus summation L going from 1 to Q, BL Z minus L, divided by the denominator, which is 1 plus summation K going from 1 to P, AKZ minus K. Okay. So this is not necessarily a filter. Here we are trying to model the human body, the human physiological system, by treating the output signal which we normally get as xn, and we are assuming a hypothetical input trigger as un. Okay, when we do this thing, we find out this expression, equation 2, looks some kind of an IAR filter. Yes, we have seen that before. Infinite impulse response filter, because it does have a numerator polynomial, and it also has a denominator polynomial, and this goes back to our classical filters. So that's why I keep telling that we are connecting these two ideas now. Filter theory, which was developed independent of any biomedical things in mind. Now we are using that concept to talk about the model, or about the human body in the form of h of z here. Okay. Now we can simplify two things from this equation 2. If we make AK 0, which in other words, if the denominator coefficients A's are 0, then that leads to a numerator which is all zeros. Okay, and that all zero is also known as a moving average model. Okay, when the denominator is just 1, in other words, your A's are 0 and you have only 1, then you have only numerator polynomial, you have zeros, and that's called the moving average system. We know from our earlier thing, it's similar to an FIR system, finite impulse response system. You just have the numerator, there's no denominator, you have only zeros in the system, and you don't have to worry about stability. Okay, so that's the important point here. The second thing is that when we assume the numerator coefficients are 0, then you will end up in an expression which has 1 in the numerator, and you will have a denominator polynomial which could be factored, and you will have an all-pole model. Okay, all-pole model. Okay, and the all-pole model, the name of the all-pole model is known as autoregressive model. Okay, it's known as autoregressive model. So two models are possible: all zero model, all pole model. When you have both poles and zeros, then we could combinedly call this as an autoregressive moving average model, or ARMA model. Okay. This is important. So when we talk about mathematical modeling, what we essentially mean, it's an ARMA model, autoregressive moving average model. When we mean it's an ARMA model, we know it's related to some sort of filter theory we have seen before. It's a pole zero model. Now, all your knowledge, all your understanding that you have from pole zero diagrams, Z transform, they all coming in very handy, because now the filter coefficients which we have seen before are starting to behave like model parameters. Model parameters. Okay, it's a super analogy, I would say. I mean, it's a great connection between what we have seen before. Now these coefficients, essentially the coefficients here are only two types. You have B's and A's, the numerator denominator polynomial. They are now starting to be taking this shape, which could be seen as pole zero, and it will allow us to do a modeling of a given system. Okay, so we will realize soon that model parameters are one of the best features that one could extract. Okay, in order to represent the signal in a very fewer dimension, and the model coefficients are very interesting and important. We know over many years that among the ARMA model, though ARMA model has both numerator and denominator, we could easily model most of our physiological system just with the poles. So all pole model is very widely used in pretty much in all of the biomedical signal application. Either you take your vibration signals, your EMG signals, or your speech signals, or for that matter, ECG, phonocardiogram, even EEG. It's been shown that the all pole model will do the job that's needed. We don't have to even go to the level of ARMA model. Okay. ARMA model is ultimate. It does cover both poles and zeros, but it's been shown that pole is good enough in many biomedical modeling applications. Okay, so what is this all pole model is now I'm just going back and doing some changes to the equation one. In the equation one, it happens that your BLs are zero in equation. If the BLs are zero in this equation one, then the all pole model could be represented by this expression, equation 3, which is basically based on the past values of the signal itself plus GUN. Okay, and this is very simple follow up, and also by rearranging these coefficients and comparing with what we have seen with prediction. Okay, so as a recall, we have seen the prediction expression before. This is coming from our derivation just now. This is a prediction linear prediction equation that we saw before. Okay, and in the linear prediction equation, En was nothing but the difference between the desired and the output of the filter. Desired was Xn itself minus the filter of the past values. So this is what we had before. Now I can rearrange this equation by just taking Xn out and moving En there. So it's basically the linear prediction equation is just simply rearranged in this way. Now you see here, this is where it gets very interesting. Okay, so let's call this as equation 3a. So if you compare equation 3 and 3a, what do you infer from those two? Equation 3 was coming out of the modeling exercise. Okay, we started with pole zero model. Then we realize, okay, let's only work on all pole model. So that's what equation 3 expression is about. All pole model. It's a model. Okay. Now, before we started talking about modeling, we talked about the general concept of linear prediction, and the linear prediction expression, which is the equation 3a, looks like that. Okay. So both have xn. Both have xn in it. Now, if you look into this equation very, very carefully, you will see that your model parameters, which are AKs, are nothing but negative of the predictor coefficients, alpha k's. Okay, and the hypothetical input that we assumed UN with the gain G, so in other words, GUN is equal to EN when you relate equation 3 and 3a. So there you go. So now what we are implying here is that the moment you estimate a predictor coefficients, okay, just finding out what the next sample would be, the predictor coefficients, alphas, you take the negative of this thing, you get your AR coefficients or the model coefficients. Okay, very, very important here. This is an outstanding result. It's because in most of the biomedical signal classification problem, I don't have to take the signal X, normal, abnormal, and to classify it. Okay, We know we can go one step further, extract the features and do it. And rather than extracting features, which we have already been exposed to, many features we know how to extract, you could extract just A's, okay, coefficient A's, and that could be used also for machine learning application to classify normal, abnormal. The important advantage is that here the case, number of case is only P, order P. Whatever is the filter order P would be P here, okay? So you only need P coefficients to classify your signal. It's some form of a dimension reduction, some form of a compression. So the entire signal, your physiological signal, which was X, which had a dimension of N, for example, and N could be large, as you know, if you're acquiring the signal for long term. I will just do a modeling. I will extract the model parameter AS, and I will be using my AS for classification application. Okay, so that's why this is one of the most commonly used feature extraction technique available out there. Okay, now how do you implement this in MATLAB? There are many ways to implement it. I mean, you can run predictor algorithms or LMS to do it. They're all connected to each other. In addition, there is also just one command in MATLAB called LPC. Okay, so when you do a command called LPC in MATLAB, it's called linear predictive coding. LPC, you give a signal X and you give the order P, and you send it to the variable A. You will get the A features from the signal X being loaded into your variable A, which becomes your new feature or model parameters. One line command, so whatever we have seen so far. Okay, so the idea is very, very neat and simple. Neat and simple in the sense, like, we familiar with adaptive filter concepts, then we made a special case of adaptive filter in the form of predictor, and I estimate the predictor coefficients, and I just take the negative value of it, which is not a big deal in feature extraction, because the signs, as long as you change the signs consistently throughout, it doesn't have any impact on the discriminatory ability. So by just taking the negative of this thing, we got AR coefficients, which are model coefficients. Okay, these three key steps allows you to have a better representation of your signal in terms of features as compared to some hybrid combo approaches that we could have done before. Before, we were extracting features based on things like zero crossing rate, your beats per minute, heart rate, form factor, coherence. Those features were extracted, but it was very hard to tell whether they are representing a signal X, because they were derived from the signal X. And also, you will realize the features which we extracted before, from the features you cannot reconstruct the signal back. Okay, whereas in this case, you give me your A's, I can reconstruct the signal back. Okay, the signal reconstruction is also possible. That's why this is such a powerful approach to that. Okay, now we could put this whole all pole model, just like how we have seen, into a transfer function. Transfer function is just a Z domain representation, and it kind of tells you again that you have only the denominator polynomial. It's an all pole model. It just says it's an all pole. So the word is used interchangeably. All pole model or AR model is interchangeably used. AR model. Some people even call to some extent it's a linear prediction model. Okay, and we know it's all connected because linear prediction and AR are connected by just that simple AK is equal to negative alpha K expression. So they all mean the same. At the end of the day, all three represent your signal in a pretty lossless way from the information content point of view. So we don't need the whole signal. We need only this P of those AKs to represent your signal, and G, we will come to that point. G is a gain parameter. In most applications, the gain parameter G is assumed to be 1. Okay, and very rarely in signal classification application, an amplitude scaling will have an impact in your classification accuracies, because it really looks into the variation in the signal rather than absolute amplitudes of the signal. As long as you have a consistent way to acquire your signal and you do a normalization, the G or any gain becomes irrelevant for machine learning applications. So here G is assumed to be 1, and there is a reason why G is equal to 1 also. We will realize that later. But you could see here, this whole thing about the modeling is just boiled down to A. So once you have this model, now this is a mathematical model. So now I'm telling from the ECG signal, this is your heart mathematically speaking. If you have your EEG signals, I'm telling this is the functioning of the brain, H of Z. So this is quite remarkable because we are taking a biological system and putting a mathematical equivalent to that, okay, with a lot of assumptions again, but it works in most of the cases. Okay, assumptions are here. We assume the system is linear. We assume to be time invariant. Convolution is the underlying expression. Then we are having poles. So that's what we have done. We have used the available mathematical knowledge to fit a mathematical model like H of Z to a physiological system. Okay, again, we have come close to it. Have we nailed the problem? Not yet. Okay, there are a lot of room for us to work on these specific aspects of it. Okay, later we will come and see that what we designed so far is essentially given hypothetical input UN, and we were getting XN, and this is what we determine as model or AR model. And as the name suggests, this is an AR model generator. We could also have the reverse process. Okay. It's called the AR process analyzer, which is nothing but it's an inverse system. You are familiar with inverse system from some of the previous examples we have seen. So what happens if you give your ECG or your signal XN as an input to this A of Z, which is nothing but the inverse system, which is nothing but 1 over H Z. Okay, so now it has become an all zero system. Then the output of that one, just from simple theory that we have seen before, you will get that hypothetical input. Okay, why it's important is that if you know your model H of Z, you could get A of Z, and once I know A of Z, I can also try to get an understanding of the hypothetical input that's driving your physiological signal. Okay, we know as biomedical engineers there are action potentials which are playing a role, but we wanted to see from mathematics and from signal processing, does the UN to some extent relates to our physiological understanding whether they are action potential. Okay, so that's another gap that could be filled because it's a lot of basically, a disconnect between people who are doing this kind of modeling and people who have thorough background about physiology. Okay, so this is where you as a biomedical systems engineer will become pretty handy in these kind of understanding and interpretation of what's going on. The interpretation understanding really comes in handy when the process is going through a pathological phase. Okay, in normal physiology, no problem, but when a pathological process is happening, what is going to happen? It's nothing but your poles are starting to now deviate. Okay, in the pole zero diagram, your poles are starting to fluctuate, and that is kind of pointing to the process deviating from a normal behavior. And now you see the pole which we have seen before from a filter theory is allowing us to characterize whether there is something good or bad happening in the human body. Okay, so we will come back and we will look into other ways of extending this similar approach of modeling and basically see the various advantages that could be obtained through this process of autoregressive modeling linked to prediction, and which is also linked to filtering. So as I said, we are now starting to connect the dots and things are falling in place in terms of providing this important link between engineering and biological systems.